Welcome to Study Loop.
Hello friends, here it is given. A gas refrigeration cycle. With two stages, compression, with intercooling, using air as working fluid. We have to find coefficient of performance of the system and mass flow rate. Property to be used of the air, specific heat 1.005 kilojoule per kg per Kelvin and adiabatic constant 1.4 using temperature pressure relation for adiabatic process. Temperature of second state of adiabatic process, you will get T1 into P2 upon P1 to the power K1 minus 1 K minus 1 upon K. Temperature of first state is given in the problem, that is 249. Compression ratio of pressure is given in the problem, that is 3. 1.4 minus 0.4 upon 1.4. So temperature of second state in isentropic isentropic process, you will get 340.8 Kelvin. Temperature of fourth state in isentropic process can be defined as T3 into P4 upon P3 whole to the power K minus 1 upon K. Temperature of third state is given in the problem, 278 Kelvin. Compression ratio of pressure is 3. 1.4 minus 1 upon 1.4. So on solving it, temperature of fourth state in adiabatic process, you will get 380.5 Kelvin. Similarly, temperature of sixth state in adiabatic process, temperature of fifth state into temperature of 6 upon pressure of 6 upon pressure of 5 K minus 1 upon K. Temperature in fifth state is given 278. Pressure ratio is 1 by 9. This is given in the problem, 1.4 minus 1 upon 1.4. So it is to be 148.4 Kelvin. To calculate the actual temperature at fourth, second and sixth state, we have to use the efficiency of Carnot cycle and turbine. So efficiency of Carnot cycle can be defined as enthalpy of second state in adiabatic process upon H1 minus H1 upon H2 minus H1. Efficiency of Carnot cycle is given 0.85. This can be converted into temperature, that is temperature of second state in adiabatic process, temperature of first state, temperature of actual temperature of second state minus temperature 1, putting the value. Temperature of second state we have measured 340.8. Temperature of first state is given 249. Temperature of second we have to calculate upon 249. So it is to be 357 Kelvin. Similarly, temperature of fourth state we can measure H4S minus H3 upon H3 minus, sorry, H4 minus H3. In terms of temperature, you may write T4S minus T3 upon T4 minus T3. So solving this equation, temperature of fourth state, you may write T3 plus T4S minus T3 upon Carnot efficiency. Substitute the value. T3 is given 278 plus temperature of fourth in adiabatic process 380.5 minus temperature of third, that is 278, efficiency is 0.85. So temperature of fourth state actual temperature we will get 398.6 Kelvin. Similarly, we can obtain the actual temperature in sixth state. For that we require the efficiency of turbine, which is defined as enthalpy of fluid in fifth state minus enthalpy of the fluid in sixth state. Enthalpy in fifth state minus enthalpy in sixth in adiabatic process. So in terms of temperature, T5 minus T6 upon T5 minus T6S. So from here T6 can be written as T5 minus efficiency of turbine into T5 minus T6S. Now putting the value, temperature T6 we will get 278 minus efficiency of turbine is 95%, that is 0.95. 278 minus 148.4, so we will get 154.9 Kelvin. To calculate coefficient of performance, we require net work done input, which is defined as work input to compressor, both the compressor 1 and compressor 2, minus work out of turbine. So it is to be H2 minus H1. This is the work in of first compressor plus work in of second compressor H4 minus H3 minus work output of turbine H5 minus H6. Amount of the heat absorbed at low temperature, that is H1 minus H6. So coefficient of performance, you may write amount of the heat absorbed at low temperature upon total work input. So we can write H1 minus H6 upon H2 minus H1 plus H4 minus H3 minus H5 minus H6. In terms of temperature, we can write T1 minus T6 upon T2 minus T1 plus T4 minus T3 minus T5 minus T6. Substitute the value. You will get T1 minus T6 249 minus 154.9. T2 minus T1 357 minus 249 398.6 minus 278 minus 278 minus 154.9. So on solving it, coefficient of performance you will get 0.892. Now mass flow rate of air can be defined as rate of refrigeration to be defined as mass flow rate specific heat into change in temperature from first to 6, so T1 minus T6. So mass flow rate you will get rate of refrigeration upon Cp into T1 minus T6. Substitute the value. This is rate of refrigeration is given in the problem, which is 45,000, but it is kilojoule per hour, so it is to be converted into kilojoule per second. Kilojoule per second. Specific heat 1.005 kilojoule per kg per Kelvin into change in temperature 249 minus 154.9 Kelvin. So mass flow rate we will get 0.132 kg per second. That's all for this problem. Thanks for watching it.